So we are discussing periodic classification, and we are discussing the most important topic, that is Lanthanide contraction. Well, I would like to remind you that any entrance test which you are supposed to write it, I think you will be getting a volley of questions in this. So the subject points are important. Please understand this, right? As far as lanthanide contraction is concerned, please understand the elements that follow lanthanum are called lanthanides. But technically speaking, I think 57 to 71 are called lanthanides. But remember that in lanthanum itself, I think the electron is entering 5d1, but it doesn't enter what? F. So the 58 to 17 elements are removed from the mainframe of the periodic table and put at the bottom, not the lanthanum. Not the lanthanum. So lanthanum belongs to the 6th period, and its configuration is it just enters 5d, right? And from there onwards, 58 to 71, the F is being filled at the bottom. Please understand that, right? And those can be called as the F block elements, but technically, I think lanthanum family would like to include the lanthanum 271. But remember that in lanthanum, I think the electron is not there in the F orbitals. It is not there. It is not an F block element, and it is a D block element. But technically speaking, lanthanides would like to involve 57 to what? 71. 57 to what? 71, you must understand. Right? So, what is lanthanide contraction? I would like to write it, rewind, and then you have n number of properties. Each property which I would like to tell is a question in the exam. Right? Observe carefully here. Now remember, decrease of size. In lanthanides. Decrease of size in lanthanides, that is approximately 0.2 angstroms on average. Remember that. There is a decrease in size in lanthanides, and the average is coming to around 0.2 angstroms, which cannot be discounted. Mind you that it cannot be discounted. Right? I'll tell you the exact values, but remember this cannot be discounted because this has a bearing effect of n number of properties, whether it's physical or chemical. Right? So there is a gradual decrease of size in lanthanides, that is around 0.2 angstroms on an average. And if you look into the reason, that is because of the poor shielding effect, it's poor shielding effect of F subshell. You must understand. So there is a decrease of size in lanthanides from 57 to 71, starting from lithium, which is the electron is entering D, and from there onwards 58 to 71, there is a gradual decrease in size till 71, and that size is up for discussion because the values, the decrease is around 0.2 angstroms on an average, which cannot be discounted. Because that has a great bearing on what? The physical and chemical properties. And why there is a 0.2 angstroms on an average decrease of size, the reason for that is a poor shielding effect of the F subshell. And we know very well that the F subshell has a very peculiar diffused shapes. That's how I describe. I describe the F subshell to be having a peculiar diffused shapes. What do I mean by that? You can just imagine that the F subshell is having pores, and the nuclear force of attraction is basically not shielded properly, and that's falling on the ultimate shell. You must understand. Now remember, if you actually see the lanthanides, general configuration, this is the ultimate shell 1 to 2. This is the penultimate shell D, 0 or 1, and most of the electrons are added for here. You can see here 1 to 14. So you can actually three subshells being what? Filled here. Ultimate, penultimate, and anti-penultimate. 3 subshells are being filled. Yesterday I was telling you this. 3 subshells are being filled. Ultimate, penultimate, and anti-penultimate. So this ultimate is the outermost shell, and you almost have no electrons in D. You don't have electrons in D. No electrons in D, you don't have a permanent D subshell over there. Electron itself is a shell. No shell, no electrons, no electrons, no shell. So you can actually say that the D is nowhere here. And I think the bulk of the electrons are added toward the F subshell, and F has a very peculiar diffused shapes. And due to that, the nuclear force of attraction, when you actually move from 58 to 71 in the 4F subshell, most of the electrons are added here. So, but this being a poor shielder, the nuclear force of attraction penetrates and falls on S. So what happens is, starting from lanthanum, that is 57, and then 58 to 71, you actually see a decrease in size. You basically see a decrease in size from lanthanum towards the 71, that is lutetium. And that contraction, we call it to be what? A lanthanide contraction, you must understand. So if I am putting it properly, right? Remember, we are discussing lanthanide contraction, which is exclusively important, and you can bank on it. The questions will come on it. And what are the questions? I'll be highlighting in the due course of my discussion. But remember, lanthanides include the lanthanide family, which includes technically from lanthanum to lutetium. But remember that in lanthanum, the electron won't enter F. It won't enter F, you must understand. It still remains to be D. So lanthanum is basically a D block element. So it remains in the 6th period and the D block. You must understand. So be clear, lanthanum is a D block element. But lanthanides family will be including 57 to 71. But from 58 to 71, they are placed toward the bottom of the periodic table, which is removed from the main frame and kept. Please understand this. Please understand this, right? Please understand the D1 series in the D block, please understand the ND1, you have 3 series, 3D, 4D and 5D. You have 3D series, 4D series and 5D series. Understand where is the lanthanum. Let me be clear. Right, in the D block you have 3D series, 4D series and what? 5D series. This starts from scandium, yttrium, and here is lanthanum. Remember that that's lanthanum. So lanthanum is basically belonging to what? 5D, and it belongs to the 6th period. It belongs to what? 6th period, because this 3D will be the 3rd period. This is the 4th, sorry, this is the 4th, this is the 5th, this is the 4th period, this is the 5th period, and this is the 6th period. So basically in D block you have 3 series, 3D, 4D, 5D. Right? The 3D series starts from the 4th period, and the 4D series will be starting from the 5th period, and the 5D series will be starting from the 6th period, remember. So you can actually see the lanthanum with atomic number 57 is basically belonging toward the 5D. But lanthanides family might include 57 to 71. You must understand. So lanthanum is basically a D block element belonging to 5D series. Now, what is lanthanum? If you wanted to highlight, then lanthanum is belonging to the 6th period, atomic number 57, and it belongs to the 5D series. It is not an F block element. It is not an F block element, mind you that. So basically, if you look into this, this is a D block, but 58 to 71, I think you are filling what? The 4F, which are placed down as lanthanides, you must understand. These are lanthanides, but technically speaking, the lanthanides family includes the lanthanum that is 57 to 71. So if you wanted to compare any properties like atomic radii or whatever, I think we include lanthanum and then do it. Please understand. But I wanted to be clear here, the lanthanum is a D block element. The lanthanum is basically a D block element. And then lanthanides are what? 58 to 71, they are F block. You must understand. But technically they will be considering it from 57 towards 71, because I just wanted to compare how the size varies from lanthanum to what? The lutetium, that is 71. You must understand. So when you're doing periodic table, the D block will be having 3D series, 4D series, 5D series. The 3D series starts from scandium, the 4D series starts from yttrium, and the 5D series starts from lanthanum. So clear. So lanthanum is basically a D block element. It belongs to what 5D series, atomic number 57 and 6th period, right? After 57, you have 14 elements missing. That is 58 to 71, where the 4F series, the F subshell is being filled. You must understand, the F subshell is being filled. But the lanthanide family might include the lanthanum, including these 14. So 15 elements constitutes the lanthanides. Technically, you must understand, but this confusion must be avoided that lanthanum belongs to what? A 5D series of the 6th period, whereas this 14 plus this is considered to be what? Lanthanides. This is the clarification which I am making it very clearly to you, right? After you know what is lanthanides, then understand that, please understand, if that is the case, then understand that, F has this, the general formula of lanthanides will involve, remember this is NS 1 to 2, N minus 1D 0 to 1, N minus 2F 1 to 14. That is the general formula of what? Lanthanides. And if you remember, this NS is called the ultimate shell. When I say it is ultimate shell, this is the outer shell which we are speaking of. That is the outermost shell. We did not consider D because you hardly have any electrons. No electrons, no shell. No electrons, no shell, no shielding. We did not discuss. D subshell is not permanent without electrons. They are not like roads which are available outside, where without vehicles also the road won't disappear the next day. It's not like this. No electron, no shielding. So hardly have any electrons, N minus 1, D 0 to 1. Either it will be 0 or 1. That's all. Right? Whereas, so this is N minus 1D is basically penultimate. And then this is N minus 2F, which is called the anti-penultimate subshell. Anti-penultimate subshell. You must understand, anti-penultimate. And here, the bulk of electrons are added. Bulk of electrons are added from 58 to 71. And here, the 4F series is being filled till 4F14. You must understand that. That is how the lanthanide configuration is. You must understand. Right? So, basically, 3 subshells are being filled. And when you move from left to right, the bulk of the electrons are added to the F. But this F is being a poor shielder. Whenever you take one step from left to right in the 4F subshell series, then I think the size is actually decreasing because this fellow is unable to shield. So the nuclear force of attraction straight away falls on this. Right? Nuclear force of attraction falls on that, and thereby the outermost shell is pulled inwards, resulting in a contraction which is very much significant and cannot be discounted, because this decrease is around 0.2 angstroms on an average when you move from left to right in the 14 elements of the lanthanides. You must understand. Since this is significant and cannot be discounted, the reason why we cannot discount this is basically it affects so many physical and chemical properties, which I would like to discuss it for you. And for that, I call this to be consequences. So let me be clear. So I was clear. So consequences, let us discuss one by one. The consequences of lanthanide contraction. consequences of lanthanide contraction. You must understand. What are the consequences of lanthanide contraction? Now, the first one, what I will say is, the first one is they will exhibit variable valency. They will exhibit what? Variable valency. Remember that each application which I am quoting now, each applications which I am writing now is a question in exam, whether you are writing it a mains exam or an advanced exam. So I draw the attention of everyone. Remember this. The first one is basically, I am speaking of variable valency. Now remember, what is variable valency? Is if you look into the general configuration of lanthanides, look into the general configuration of lanthanides. General configuration, it is somewhat like this. It is NS1 to 2. I draw the attention of everyone, please. And this is N-1D 1 to 10. And this is N-2F1 to 14. This is the general configuration. Now, remember, when we are speaking of lanthanides, we are almost to the 6th period. And each period is a shell in what? Periodic classification. Each period is a shell designated with a principal quantum number proposed by Bohr. And N1 to N is equal to infinity. You have infinite number of shells, so you can expect infinite number of what? Periods. And we are to the 6th shell. We are to the 6th shell means we are very far away from the nucleus. If this is the nucleus, this is the first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. That means that you are almost far away from the nucleus. When you are far away from the nucleus, the energy difference between the shells decreases. In fact, if you recollect the Bohr's theory, in fact, we were telling that the energy difference decreases and delta E basically tends to 0. The energy difference basically tends to 0. So this belongs to, these lanthanides belong to what? 6th period. 6th period. When it is the 6th period, the energy is very, very what? High. So I can expect that, you know, I can simply say the delta E, that is nothing but the energy difference, between these subshells, between N-2F, or I can simply say F, D and S is very, 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 very less. You must understand. The energy difference between this subshell and this subshell is absolutely very, very less, because we were told in Bohr's theory, as you are far away from the nucleus, the energy difference between the shells decrease. The energy difference between the shells decrease. When energy difference between the shells decrease, energy difference between the subshells also is expected to decrease. So the Aufbau principle, which we are speaking of, starts violating or gets violated mostly in what? When you go far away from the nucleus. So Aufbau principle on which you are writing the electronic configurations, you don't find any violations in the initial periods, you must understand. But as you go far away from the nucleus, there is every violation. And in fact, ridiculous is what Aufbau's principle when you go far away from the nucleus. And one classic case of the violation of Aufbau principle, we get it from what? Lanthanides, because lanthanides belong to what? 6th period, we are very far away from the nucleus. So if someone is asking you, why lanthanides exhibit variable valency? Now, first of all, what is variable valency? If you see sodium, it will show only a monovalent ion. So it's monovalent, Na+. You don't see Na+2, Na+3, Na+4. It has only one valency, univalency, that is monovalency. That's all. You can't have the +2. Remember why? Because our teacher told us very clearly, if you write its configuration, so it's 1s2, 2s2, 2p6 and 3s1. This is the outermost electron which you removed. That is, the electron has been removed from the third subshell. So it will develop a positive charge. Now people might ask me, why don't you remove one more electron from here, such that it forms Na plus 2. You can't remove. Our teacher was telling us because it achieved a noble gas configuration here. That is, you can see here neon gas configuration. That's what she told us. She or he told us in school. But let me tell you that the energy difference between the third subshell and the second subshell is too high. I draw the attention, please. If someone is asking us why alkali metals don't exhibit variable valency, is the question, then what you are supposed to do is write the electronic configuration. You can see the electron has been removed from the S subshell, that is the outermost subshell, NS1 in alkali metals. And if you try to remove it from the one more electron, then I think it has achieved the noble gas configuration, or otherwise in energy terms I can say the energy difference between the outermost shell and the next shell is too high. Is too high. Rather we get a jump in ionization potentials, you must understand. Is basically very, very high. So removal of the second electron seems to be absolutely not possible. It is not possible. So sodium will show only monovalency. All alkali metals will show what monovalency. This term variable valency, you see it starting from D block, and there is everywhere in what? F block. Why D block? Because D block starts from the fourth period. So you are basically far away from the nucleus. And when you start going far away from the nucleus, the energy difference between the shells will decrease. And of course, the energy difference between the subshells would like to decrease. That's what it is. So the Aufbau principle significance will be fading off when you are actually far away from the nucleus. Exactly opposite of what we are telling here, that the 3s, the energy difference between the 3s and the second shell is too high to remove the second electron. But that's not the case here. You look here. The energy difference between this ultimate, penultimate and anti-penultimate is basically too less. Very less, in fact. Very less. When the energy difference between these is very less, then it implies electrons from S, D and F can be removed, can be kicked out. You can remove electrons from penultimate, ultimate and anti-penultimate because the energy difference between them is what? Very less. The subshell's energy difference is very less. That's not the case here because the energy difference between the third 3s and the second subshell is very high. So removal of electron from the second, from the third is very high. So you can't do it. So alkali metals don't show variable valency. But here the case is they exhibit because the energy difference between the ultimate, penultimate and the anti-penultimate is basically what? Very less. So the electrons from any of these subshells can participate in bonding. Any of these subshells can what? Participate in bonding. You must understand. Here is an advanced level question which he will be asking in exam. Now this question is basically a knowledgeable thing. It doesn't involve any great intense concept when you actually wanted to prepare for the advanced level exam. Now what he is actually testing you by asking this question is basically, did you go through the textbook? Did you go through the textbook, each and every line, such that you have some information regarding lanthanides? That is the only motto. Normally, studious students, of course, they will be underlining everything with the pencil, the NCERT book or the reference book which is given for what? JEE Advanced. So, this is a basic test. Now remember that this comes under what? Variable valency. It comes under what? Variable valency, and it's an advanced level question which says, which of the following is true? That is the question. Which of the following is true? That is the question. Right? And if which of the following is true, if you wanted to answer, you need to read everything, every line that is given under what? The variable valency under what? Lanthanide contraction. Well, I would like to write that for you and remember till you write your exam. Watch carefully here, the one which I am writing. Normally what happens, lanthanides generally exhibit. They exhibit +3 oxidation state. Normally, all the lanthanides will exhibit what? A +3 oxidation state. You must understand. Most commonly noticed oxidation state among lanthanides is +3. So you have lanthanum +3, you have cerium +3, you have lutetium +3, fine. But remember, this is not alone the oxidation state. We are speaking of variable oxidation states. That means you have more than one oxidation state. So what I'm commenting on is basically the +3 oxidation state is more common in lanthanides, whereas even +4 is also shown. After all, they exhibit what? Variable valency. The +4 is also shown. And I can write some elements. A +4 is given by the element which is PR, ND, TB and dy. So he will be very specific. This sounds actually trivial, but remember that, whether we have great applications of plasmodium and neodymium and terbium and dysprosium. These elements are very rare, but still he is testing in advanced level exam, the JEE advanced level exam, whether you are studious or not. Did you spend time before books or not with a pencil underlining each and every line in Lanthanide contraction? Are you serious student or not is being tested. And remember, which of the following is true if he is asking? The general oxidation state is what? +3, but there are four elements which will exhibit even +4. So you basically can remove 3 electrons from lanthanides. At the same time, it exhibits variable valency where you can actually pull 4. Right? Because every subshell is participating in what? Bonding, because the energy difference between all the 4 is what? All the 3 is what? Lesser. So what are the +4 oxidation states? He's asking very specifically. Then remember, these are the 4 elements, right? Plasmodium, neodymium, terbium and dysprosium, you must understand. So it is PR, ND, TB, dy. So it is PR, ND, TB, dy is the +4 oxidation state which is shown by what? Lanthanides, you must understand. But otherwise, generally, they show what? Generally, they show +3 oxidation state. You must understand why this discussion is cropping up. First of all, understand few things. We are discussing about what? Variable valency. Variable valency is only exhibited by D block and F block. It's not exhibited by S block and P block, you must understand. Mostly exhibited by what? D block and the F block elements, because D block starts from the 4th period and the F block will be starting in the 6th period, you must understand. 4 and 6 are basically far away from the nucleus. They are basically far away from the nucleus, and when you are getting far away from the nucleus, the energy difference between the subshells is basically decreasing. So your so-called Aufbau's principle, on which there is hierarchy of energy levels should be filled, is basically what? Is not viable when you are actually going far away from the nucleus. That's why D block elements also exhibit what? Variable valency. Like ferrous exhibits Fe, iron will exhibit Fe+2 and Fe+3, ferrous ferric. You must understand, copper, cuprous and cupric. So you always have variable oxidation states when you are actually far away from the nucleus, which is more common in D block and what? F block. In F block, everywhere you have variable valency. Coming specifically to lanthanides, the common oxidation state is basically +3. And +4 is also exhibited by 4 elements, and I wanted students who are preparing for the exam better mug these elements, because they have nothing to do with your research paper. You will never do it so early. So just writing for the examination's sake, you must be remembering that's nothing but what? PR, ND, TB and dy. PR is plasmodium, neodymium, terbium and dysprosium. You must understand they exhibit +4 oxidation state, which will be asked in the exam. You must understand. That is the first consequence of lanthanide contraction. They exhibit lanthanides. You can say not exactly contraction, some properties of lanthanides which I am telling you. The consequences are also there, we would like to discuss. Right? So all properties exhibited by D block are exhibited by F block. D block exhibits a variable valency, and F block also exhibits what? Variable valency, which I am highlighting it, right? Let us go and see what are consequences of lanthanide contraction. Let us see the second one. So we are, that is the first property, that is variable valency. You must understand. And that question, each and every question which I am discussing right now, after telling you what is lanthanide contraction, will be coming in exam. Whether it's a mains exam or advanced level exam, the previous one exhibiting variable valency is an advanced level question which he will be testing your knowledge rather than the concept. You must understand that. That is the first. Second, what I'm telling is, second property is basically complex forming tendency. Complex forming tendency. You must understand. Complex forming tendency. Well, we complex forming tendency, if you look into the entire periodic table, the complex forming tendency is only for very few people, not for all in the periodic table. It will be ridiculous on our part to check alkali metals existing in a complex. Now, what is a complex, first of all? What is basically a complex? A complex, where you have a dative bond. Any substance which has a dative bond. What is a dative bond? A coordinate covalent bond. You give a pair of electrons, we both share. Such a covalent bond can be called as what? A dative bond, or a complex compound, or a complex salt, you must understand. So basically, complexes are those substances which will be having a coordinate covalent bond. Now remember, in the entire periodic table, complex forming tendency is 0 for some elements. They don't form complexes. But the complex forming tendency is more intense for some compounds, for some elements in the periodic table. So if this is the diverse way of this tendency, then it is prudent on our part to basically investigate complex forming tendency. Basically depends on what factors. Then we would like to paint this concept to the lanthanide contraction, and hence the question, right? So complex forming tendency, what are the factors? First of all, understand a complex is that substance which has a dative bond. You must understand, a dative bond. When I say dative bond, I'm speaking of coordinate covalent bond. It's basically coordinate covalent bond. So if someone is asking you, what is a complex? Then you tell them that you check it out. If you have a dative bond, it's said to be a complex. And what is a dative bond? If you recollect, one of the atoms which is participating in the bonding will be donating the entire pair of electrons. Normal covalent bond is you give one, I give one, we both put it at the center and live happily. That is the philosophy of what covalent bond. Here, the donation of the pair is done from one of the atoms that is participating in the bonding. So you must understand. So the donation is the issue, right? Otherwise, if you actually recollect, right, establishment of the covalent bond is done between a Lewis acid and a Lewis base. It's basically between a Lewis acid and a Lewis base, a coordinate covalent bond is established. So acceptor and the donor. And the donors are basically what? Lewis bases, and the acceptors are nothing but what? The Lewis acids. And then the coordinate covalent bond is established, right? If this is the philosophy of dative bond, then I think we must be writing the criteria. Not all criteria, I would like to write the basic criteria for complex formation. Basic criteria for the complex formation. I have two things to do. One, as I said, a pair of electrons is donated to you. When a pair of electrons is donated to you, you must be accepting it. For acceptance, you don't put electrons in your pocket, right? You need to have empty shells. So you must have vacant subshells, or vacant orbitals, you must understand. So the first criteria is empty yourself. You empty yourself. When you are emptying yourself, then I think the pair of electrons can be donated to you. Emptying yourself in the sense, after all, lanthanides are basically metals, and metals exhibit positive oxidation states. And emptying yourself means kicking some of the electrons from your general configuration, ultimate, penultimate, anti-penultimate, what I was writing. So you empty yourself such that I can accept what? A pair of electrons being donated by the Lewis base, which I consider it to be a donor, right? So criteria for complex formation is vacant orbitals such that I can accept it. And the second most important, the size of the central atom. The size of the central atom, that means the acceptor, or I call this to be a Lewis acid. A Lewis acid, the size of the central atom or the acceptor. The acceptor, you are donating the Lewis base, donating a lone pair to a Lewis acid and establishing a coordinate covalent bond will result in the formation of complex. And if I can write it for you, if you just recollect, Lewis base, which I call this to be a donor, is donating it to the Lewis acid. So you have one way, that is how the coordinate covalent bond is shown, and then this will be the acceptor, and that results in the complex. So these two comments which I am making, that it should have vacant orbitals and the size of the central atom, that means I am referring to the Lewis acid. The acceptor. Acceptor plays a critical role. Someone is donating, but you should have the capacity to accept. And where will you put the electrons? You should have the vacant orbitals, right? So what are the criteria? Vacant orbitals, and the size of the central atom must be what? Small. Size of the central atom must be small. This is the criteria. Now coming to our discussion, this complex forming tendency in lanthanides, we wanted to link this complex forming tendency to the lanthanides because the question that is asked for you is which of the following is true. It says the complex forming tendency increases from left to right in lanthanides. It increases from lanthanum to lutetium. It decreases from lanthanum to lutetium. It first decreases, then increases. That's how the questions are framed, and this is a question which will be asked in exam. That will be asked in exam. So, cut it off. So let us actually apply this complex forming tendency to lanthanides and see whether the trend is increasing from left to right from lanthanum to lutetium, or it's first increasing then decreasing, etc. We'll apply this criteria, right? And remember, when you see, basic criteria is you must have the size of the central atom, right? The size of the central atom. How? You should have vacant orbitals and the size of the central atom must be small. So basically, if you wanted an element in the periodic table to form complexes, the size must be what? Small. So common sense is suggesting the first group elements and the second group elements hardly involve in complexes. Because the S block is the biggest in sizes in the entire periodic table. So if someone is speaking of potassium complexes and sodium complexes and rubidium complexes, you slap that fellow and tell him that, rubidium, potassium and sodium are the biggest sizes in the periodic table, and for forming a complex, the size of the central atom must be small. You tell him that. But very consciously, very consciously, I was taking the examples of potassium, sodium and rubidium and left out lithium. I left out lithium. Because even though lithium belongs to the first group, it is the smallest. So the complex forming tendency even in the first group, lithium will be forming some complexes, you must understand, because of its small size. So basically what I'm telling you, you have magnesium complexes also, like you have chlorophyll. In the second group also is bigger in the periodic table. So the complex forming tendency is least in first group and second group because they are the biggest, with some exceptions where the elements are placed to the top of the first and the second groups. That's lithium, magnesium and beryllium. You can actually see some complexes, and magnesium complexes are very much available in the form of chlorophyll, the green pigment in the plants. You must understand that is nothing but the central atom there is magnesium, which is nothing but the Lewis acid or the acceptor. You must understand that. So normally this complex forming tendency is told for D block and of course F block. D block and F block. Now what we are investigating is basically in lanthanides, how do they vary, right? And look into this. If this is the case, if you look into the lanthanides, For lanthanides, if you look into this, it is lanthanum, from lanthanum to lutetium. From lanthanum to what? Lutetium. From lanthanum to lutetium, right? The size, this will also form La plus 3. And from here, it also forms plus 3. Because plus 3 is a common oxidation state that we find it in what? Lanthanide contraction, you must understand. Right? So if you look into this, the lanthanum to lutetium, they both form plus 3 oxidation states, indicating that you have removed some electrons from lutetium and lanthanum and you are having vacancy. So the first criteria of having vacant orbitals seem to be met by both of this. Now, if you wanted to check whether lanthanum has a better complex forming tendency or lutetium having a better complex forming tendency is determined by the second factor. This is the differential, you must understand. The size of the central atom. Now, any positively charged species is said to be Lewis acid. So, these two are Lewis acids, no doubt about it. Now, we have to choose the fellow who is smaller in size. And remember, and this is a lanthanide family, from lanthanide to lutetium, 57 to 71. Technically, those are called lanthanides. So what happens from lanthanum to lutetium is basically, if you look into the size of lutetium plus 3, it is very much smaller compared to lanthanum plus 3. You must understand. Look into the size. The size is basically like this. The size. Why it is like that? Because of the lanthanide contraction which we see. Due to lanthanide contraction, you must understand, due to lanthanide contraction, as we discussed earlier, when you move from lanthanum to lutetium, the size is actually decreasing because of the poor shielding effect of F. So I would like to say the average decrease is around 0.2 angstrom units, and I was telling you that you can't discount this decrease of size. You must understand. You can't decrease, you just cannot discount it. So what I mean is, you require a size of the central atom must be small. So out of this, the smallest seem to be lutetium plus 3. So the complex forming tendency is highest for lutetium plus 3 and it's not for lanthanum plus 3. You must understand this. So what is the question? The question is, which of the following is basically true? Which of the following is basically true? Well, I would like to write then, if this is the case, let me put it properly, the trend for you. Watch carefully here. Well, the CFT, that is nothing but the complex forming tendency, CFT, depends on the size. And in fact, we want a smaller size of the metal atom. When I say metal atom, I am actually referring to what? Lanthanides, you must understand. The CFT depends upon the size. And that I'm referring to what, in fact, I wanted the smaller size of what? Metal atoms. And if you look from left to right, from left to right, from lanthanum +3 to lutetium +3, the size actually decreases. The size basically decreases, and that's because of lanthanide contraction. That's because of what? Lanthanide contraction. So basically what is happening is the complex forming tendency increases. This is the question. From left to right, that is in lanthanides. You must understand. In lanthanides, that is from lanthanum to what? Lutetium. This is the question which he will be asking in exam. So the complex forming tendency is increasing from left to right, from lanthanum to what? Lutetium. Because of the lanthanide contraction, the size is basically decreasing, and we require Lewis acids, the acceptors, to be smaller. I think lutetium +3 is a better Lewis acid compared to what? Lanthanum +3, because of its greater acceptance of the lone pair, because of the increased nuclear force of attraction. Because when you're small, you have greater nuclear force of attraction, so you can hold on your head more donors. So the smaller the ion, greater is the nuclear force of attraction, greater is the amount of donors which you are able to actually accept it, and thus forming complexes, and hence the complex forming tendency increases from left to right. You must understand. Right? So that's, I'm clear. Then the second, go for the third. So let us go and check out the other ones. Let us see application number. This is very, very important. This is extremely important. Extremely important. Please bank on this, and this you will get it 100% sure. You're supposed to get 100% sure question in the exam as a consequence of lanthanide contraction, or the properties of lanthanides rather. Remember, what I'm telling it is 100% sure is this. Watch carefully here. This he will ask in exam. Basic nature of hydroxides. Basic nature of what? Hydroxides. You must understand. Basic nature of what? Hydroxides is what we are supposed to discuss it. Remember, first of all, basic nature depends on what? Right? Now, basic nature, remember this point. We say metals, our teachers in REL schools, in our school, we're discussing this, and that is metals are basically bases. Or otherwise, I can simply say all metals are basic. So all metals are what? Basic. And where are metals in the periodic table? They are placed to the extreme left, and the D block and the F block. These are the metals. And all metals are what? Bases. If this is the case, well, I would like to call all good metals are good bases. I think you will agree with me. Because metals are said to be basic, so good metals exhibit more basic character. They exhibit more basic what? Character. You must understand. If this is the case, the implication from these two, what I understand, it implies basically basic nature. If you look into this, the basic nature is a function of metallic nature. You must understand. So if you wanted to choose a very good base in the periodic table, you should choose a very good metal. And great metals are placed to the extreme left, bottom rather. So you will have the alkali metals to be, hence the name alkali. Alkali metals are the best metals in the periodic table, and they would like to be more basic. They would like to be more basic. That's what it is. So I write synonymous statements here. Metals are bases. So I can say all good metals are good bases. You must understand. So basically, basic nature is a function of what? Is basically a function of metallic nature. And if you actually wanted a relation between them, then basic nature directly proportional to the metallic nature. So greater is the metallic nature, greater is what? The basic nature. That's what we know. That's what we know. Right? And if you actually think reverse, I think greater non-metallic nature, more is covalent nature. Right? So remember, whether you are more basic or less basic, depending upon your metallic nature or a non-metallic nature. If you are more non-metallic, you are more covalent, you are more basic. If you are more metallic, you are less covalent, right? Less basic. You must understand. More metallic, less covalent, more basic. Right? Less metallic, more covalent, you are more acidic. You must understand this. Then if that is the case, right, simply speaking, or otherwise I can simply say more covalent nature, then you are basically less basic. You must understand. Because when you are more covalent, you are more non-metallic, then you are more acidic rather than being basic. Well, I would like to spend some time here for you. Remember, more is the covalent character, you are more acidic and you are less basic. You are less basic. You must understand. Because all non-metals are acidic and non-metals are placed to the extreme right of the periodic table, and from left to right the size decreases. You must understand this, right? So basically this is the critical point which I would like to say. More covalent nature, you are less basic, because more covalent nature is found in more non-metallic nature. More non-metallic nature, more covalent, and then you are less basic. And covalent nature and the non-metallic nature is basically what directly related, you must understand here. So forget about all this and just remember this. More covalent, you are basically what? Less basic and more acidic. And now what I wanted you to recollect, please recollect. If this is the case, then I would like to rub this. In fact, I would like to write one statement and just go for what? The trend. What I mean is, more covalent nature, you're basically less basic. This is what is my contention. If you are more covalent nature, you will be more acidic and less basic. You are more non-metallic. And remember and recollect. Farjan rules. Farjan rules are basically told to judge covalent nature. Basically, Farjan's rules are used to fix what? Covalent nature. To fix covalent nature. What is Fazen's rules telling? He is telling, watch. He is commenting on this. Smaller the size, more is the covalent nature. Smaller the size, more is covalent nature, less is basic nature. Well, I am not surprised an iota of this statement for the simple reason, if the sizes are big, you are placed to the extreme left in the periodic table. And bigger fellows are metals, and metals are basic. So what he is basically telling is, smaller the size, that means he is referring to the people who are to the right. To the right. And they have more what? Covalent nature. Of course, they are non-metals. Non-metals do possess acidic nature, and of course they possess what? Less basic nature, he is basically telling. So simply speaking, the basic nature is the function of the ionic size of the metal. You must understand. And basic nature, in fact, is inversely related to the size of the metal atom. You must understand. The size of the metal atom, you must understand. The ionic size, rather. The ionic size. The smaller the ionic size, no, in fact, not inverse relation. Sorry, I withdraw. Basic nature is directly proportional to the ionic size of metal atom. You must understand, not inverse relation, please. So more is the ionic size of the metal atom, more is basic nature, because the biggest sizes are placed to the extreme left in the periodic table. If this is the case, well, recollect then, in lanthanides, size decreases from lanthanum plus 3 to lutetium plus 3. The size is basically decreasing from what? Lanthanum plus 3 to lutetium plus 3 because of the lanthanide contraction. So the biggest size is possessed by lanthanum. So I would like to say the size of lanthanum plus 3 is greater than lutetium plus 3. So basic nature of lanthanum hydroxide will be greater than lutetium hydroxide. You must understand. Well, remember that basic nature of lanthanum trihydroxide is greater than basic nature of lutetium trihydroxide. Because the size is decreasing from lanthanum to lutetium, you must understand. It's decreasing from lanthanum to what? Lutetium, you must understand that. So, left to right, the size decreases. Left to right, the size decreases in lanthanides. So, basic nature of hydroxides also decreases. So, if he's asking you a question, if he's basically asking you a question, this is the truth. Size decreases in lanthanides from lanthanum plus 3 to lutetium plus 3. And hence so, basic nature of hydroxides also decreases from La plus 3 to lutetium plus 3. So, basic nature of lanthanum hydroxide is greater than lutetium hydroxide. You must understand, indicating that lanthanum is a better metal compared to what? Lutetium, because the size is bigger, and if you are a better metal, then you are a better what? Basic oxide or hydroxide.